perfect. Mason, could you please go ahead and share your screen?
Okay, yeah, let me check here. Should be this one. Okay, can you see my screen?
Yes, thanks. We can also hear you well.
Yeah,
on the agenda attached, there's a Binder link, so you can follow along on Binder, or like everything is also in the GitHub repository, so you can follow along on Coffee, Casa as well. Okay, please, Mason, take it away.
Okay, yeah, that's exactly what I was going to say, that the links are here, both the GitHub repository and the Binder link. So I'll try to run on this Coffee Open Data.casa myself as well. So I'm Mason Proffitt. I'm a PhD student at the University of Washington, and I work with IRIS-HEP and do Atlas data analysis. So yeah, they will be it should be in notebooks. So I'll be doing 2 talks today. So the first one is this Uproot awkward vector demo, and the notebook. If you open the Binder link, it'll go straight to this notebook, but I'll just open it here. Okay, yeah. So this first talk will be about these 3 packages: Uproot, awkward, and vector. And it'll be relatively fast. I usually cover this in like a 3-hour-long tutorial aimed at like very much beginners in data analysis in Python. So I'm going to assume for the purposes of the talk that you're already familiar with at least Python, NumPy, Matplotlib, kind of the standard Python tools. So I've compressed the tutorial here and added a bit of advanced material, but it's still just scratching the surface.
Sorry to interrupt. Could you slightly increase the font size, please?
Oh yeah, no.
That will make it easier to follow along. Thanks. Okay, perfect. Thank you.
So yeah, there we go. With that, so yeah, first I'll talk a little bit about the motivation. So probably don't need to cover this too much, but so all of this workshop is going to be about Python. Of course, in high energy physics, kind of the standard for a long time has been C++ as a programming language, but Python has really risen quite fast in the past several years for data analysis. It's become arguably the most popular programming language, depending on your metric. So this means that there's a huge community for supporting Python, and there are many tools that are standard tools that are used in the Python community. So there's lots of support already, and Python generally is considered easier to learn and use than C++. So the first package, Uproot, so this is a Python module that can read and write files in root format. And it's part of the Scikit-HEP project, just like the other 2 that I'll be talking about. So these are Scikit-HEP is a set of tools designed to help for high energy physics data analysis. And so Uproot isn't the only way to read and write files in Python. There are other packages, but Uproot is arguably the best. And there are a few reasons. One is that Uproot is very slim. It's very focused. It only it is concerned with reading and writing root files, and it only depends on NumPy, although it works very well with awkward array and vector, the other packages that I'll be talking about. And yeah, just like the other packages, it's easy to install Uproot. You can just do pip install or conda install. It doesn't require any complex installation. It doesn't require any part of root itself. It's completely separate from the root software. It only shares the root format, the file format with root. And so Uproot is designed to be very efficient, like NumPy, in reading the root files and writing them. And we'll use awkward to perform very fast operations with arrays that are stored in root files. And yeah, okay, then I've already mentioned awkward. Awkward is basically NumPy for jagged arrays. So when we're manipulating data in high energy physics, it's often not a rectangular array of data. That is, the length of the collections is not constant across events. Different events will have different numbers of jets. Different jets can have different objects within them, like tracks. And so these kinds of arrays are called jagged. And so like there's this little sketch down here of a rectangular array where all of the dimensions of an array are the same length across the whole array. So here there are 5 elements in the 0 axis of the first dimension, and then 2 elements in each within each of the subarrays. So this has a well-defined shape, like 5, 2. A jagged array doesn't have a constant length along some dimension. So like in this jagged array, the first row has 2 elements, the second has 3, and then 1, and so on. So NumPy can't natively handle these kinds of jagged arrays. So this is where awkward comes in. It handles these kinds of arrays, just like with very similar syntax as the rectangular arrays in NumPy. And so being able to operate on an array at a time, this is the idea of columnar analysis, which is usually much more efficient than running a loop over events, or even within an event. You can do an operation on an entire column, an entire branch at a time. And then the last package that I'm talking about is vector. And this is a fairly straightforward package that allows manipulating vectors. So 2D, 3D, and 3+1D, so like Lorentz vectors. And again, you can use NumPy and awkward array with this vector package to perform Lorentz vector operations on arrays of vectors. So you can do things like calculate invariant mass or delta R on entire arrays of these vectors. Okay, so for the rest of the talk, the goal here is basically just to learn how to use these packages together. And so as kind of the motivating example, I use this very short and simple analysis to look for resonances in dimuon events. And this uses an example open data file from CMS from 2012 in order to try to look for these resonances. So to get started, okay, first we'll just want to understand how to open a file in Uproot and navigate to this information. And then I include the setup information, but that's already taken care of for both Binder and for running on this Coffee Open Data Casa. But it would be as simple as just pip install or conda install. And then we'll need to import these packages, so NumPy and Matplotlib. I'll be using those, and then also Uproot, awkward, and vector. And so just as a matter of convention, Uproot and vector are usually imported as their names, and then awkward is often imported as AK, just to shorten it, and also as an analogy to like importing NumPy as NP. Okay, so let me just try this a little better. So yeah, like I said, so the first thing that we want to start with is opening this data. So the simplest way to access information from a root file in Uproot is to use uproot.open. So we'll start here. I have this root file is in this repository already, so it should just be sitting here, whether on here or on Binder. So if we do file equals uproot.open, then we get this file object, which here is called a read-only directory. That's the class name that comes up. So in root, this is like a T directory, and it's just saying that we've opened it in a read-only way. And just like any kind of directory, you can list the contents of the directory, in this case, this file. And so this is the kind of Pythonic interface here is to use keys, so like a dictionary. So we can say file.keys, and that actually, let me think. I'm just gonna clear cells, but okay, I'll just do this just so that everything doesn't already show up. Back to where I was, yeah, here. And all above, yeah. So that comes up when we get to it. Yeah, so file.keys gives you a list of keys that are in this file. And yeah, I have the Slido open. So that's, yeah, I'll mention that. I don't know exactly how other speakers want to handle questions, but for this tutorial, I think usually if questions come up, I encourage people to put them in, and if they're relevant to what I'm talking about at the moment, I'll probably just answer it right away, because that usually works best. If it's a more higher level, like overview kind of question, then I might wait until the end. But definitely ask questions about things as they come up. Yeah, so there's this list of keys, and here there's only one, and so there's just events. This is a very simple file. It's a nano AOD like file. So the name is events, and then the semicolon 1 is the root cycle number, which we won't have to worry about. This doesn't tell us what kind of object is in there. It just says that there's one object called events. And so Uproot can read multiple types of root objects inside of files. So we can see exactly what types are in here with this class names function. And this shows that events is a T tree. So this comes up in pairs of the T key name and the object type. Okay, so this is the tree inside of this file. It's just called events. So if we want to start descending into the file and getting down to the actual data, we can access this tree by like subscripting here. So we ask for this key events, and then this will give us the T tree. And it says there's 6 branches. And so, okay, then that's one more level, and then now we can just assign this tree to an object, just calling it tree here. So, in assuming familiarity with Uproot, T trees are just essentially tables of information where the columns are called T branches, and each row, each entry in a branch corresponds to one event. This is the usual format that we're dealing with. So this tree object, we can look at the branch names by using this keys function again to see what kind of branches are in here, the columns, and then this gives us a list of the branch names. So there's nmuon, muon pt, muon eta, so on. So it just has information about muons. And right, so for each event, you'll have these event properties. And so another way we can look at this with a bit more information is tree.show. So this is kind of like ttree.print, or yeah, the print function of ttree, where it shows the names and the types of each of the branches. So here we can see nmuon is an assigned integer, and the rest of the, okay, so muon, pt, eta, phi, and mass are arrays of floats per event, and then muon charges an array of integers per event. And then we get to the point where getting the actual data from the table. We can see information about the tree. So the shortest way to get actual data from the table is to do tree.arrays. So I'll use this for now, and I'll talk about other methods towards the end. So then we can see there's this array object, and there are some numbers. You can see these branch names in here. And so I'll go through this in a second. So this has all the information from the branches. Arrays reads in all of the branch data. So I'll assign this to another object or another variable. I'll just call it branches, and then start looking into this object here and the using the branch names that we saw. So if I want to access a branch from this array object, I can subscript it like this with the n-muon key, so just the branch name. And then, okay, now we see a simpler array. You can also use you can use attribute or property notation like this, where you can just say dot and then the branch name. This will give you the same thing. So it's just another way to access the fields within this array. And so here we can see this array just has a list of numbers inside of it, at least from this representation that shows up. And so these are the number of muons in each event. And you can see it's abbreviated with this ellipsis because there are many events, so it doesn't show all the entries in here. Yeah, so this is this array object, which is really the crux of awkward array. We haven't used awkward array directly, but if you have uproot and awkward installed, the output will be these ak.array objects. And so we can start to understand how these array objects show up. So there's this type part at the end of the representation, and it shows a number times UN32. So it shows the number of entries, like the 0th axis, the length along the first axis, and then the type. So this is just a 1D array. They're saying there are 100,000 entries, and each one is an unsigned 32-bit unsigned integer. And then we can look at one of the other branches. So in this case, muon PT. And so here there's a little bit more structure. There's brackets within this like list representation here. And now there's this like star var and then star float 32. So this is saying that this is a jagged array. There's a variable number of elements in each event because there are a variable number of muons. And right, so this is basically an array of arrays, a 2D jagged array. Okay, so then that's looking at one kind of dimension, looking at a column at a time. We can also look at individual events at a time. Like maybe we just want to look at the first event, the PT in muon PT in the first event. So you can subscript these branches just like you would with a NumPy array, and then this will give you the array corresponding to the muon PT just for the first event. And so you can see the type. It's just saying there are 2 muons in the first event, and it gives you the float values for the PT for these 2 muons. Yeah, it doesn't say anywhere, but for nanoAD, the units are always GeV. And you can look at a different event, and you can verify indeed that the number of muons in the event can vary. So the third event with subscript of 2 only has 1 value here. So it's just showing that it's jagged. So you can also, this is looking at one branch and one event. You could also look at one event across all branches. So if you just subscript with a number, say branch is 0, look at the first event, then you get an object like this. So this is a record type. So this is another type provided within awkward array, and it is very similar to a Python dictionary, a dict, except it can contain more complicated structure, and you can use awkward functions on it. So yeah, again, there's a lot of information that's hidden here that's in order to fit inside this line. So one trick that you can use to display all of the information that's contained is this toList function. It's just like NumPy. Any NumPy array also has this toList function. So it'll convert to, depending on the structure of the array, it can be lists or a dictionary or some combination, like in this case. So there's for records turned into dictionaries here. So you can see this turns it into just a standard dictionary with the keys being the branch names, and then the values are the data that's within this event. So the number of muons and the muon PT. So it's just showing all of the information that's contained for the first event. And yeah, I said this, so also just like NumPy, you have to be careful about printing out, large blocks of information, or you wouldn't want to do to list on an entire large root file with all of the branches and all of the events, because then it could potentially crash, because it would just be so much information. It would certainly flood the screen. And one other way to see, if we didn't care about looking at the data directly and we just wanted to see a description of the structure, you could also do branches.type for this array, and this will give you just a type part, but not truncated. So it'll display the whole description. So that's saying there's 100,000 entries, and then basically each row is composed of all of these fields, and muon PT, and so on, and then it shows the type of these fields. Okay. So then that's getting to the point where we can access the information with Uproot and get these awkward objects out. Then the next natural step is wanting to transform the data that you pull out of these files. So Uproot is designed for columnar analysis, which is performing any analysis operations on these entire columns at a time, rather than explicitly looping over an event. So the simplest thing that you can do in columnar analysis is just look at the length, the length of a column, or the array that represents the tree. So if you do len on the branches object or any of the branches within this bigger array, you'll get an output of 100,000, which we've already seen. So there are 100,000 events. That's the length along the first axis. And so I mentioned here, so even for jagged arrays where, muon PT, where there will be more than 100,000 numbers and more than 100,000 entries, if you're counting each PT, it'll still, the length along the outer axis will still be 100,000. So in order to look at that a little more, you have to flatten an array. So if an array has more than one dimension, just like with NumPy, 2D arrays or higher, you can use this NumPy function, np.ravel, on one of these branches, and then this will completely flatten the array. So it just turns the 2D jagged array into a one-dimensional array. So it just basically concatenates all of the individual arrays within each event together to give you one 1D array. And so one thing I just note here is that, so this really is a NumPy function that's running on an awkward array package array. So most of the standard NumPy functions work fine with awkward array. It uses the array interfaces that are provided by NumPy, although there are also equivalent awkward functions. Like usually you can change the NP to AK, and a lot of NumPy functions have the awkward equivalent. And in most cases, basically the default behavior is the same between these. But the awkward versions can have optional parameters that have they can provide functionality that only makes sense for jagged arrays. And so like this is there are also functions that wouldn't make sense for NumPy rectangular arrays. So one example is like ak.num. So this is for if we wanted to count the number of individual entries of muon PT. In other words, count the number of entries within each event, and then sum that across all of the and then you can also be able to sum across all of the events. So if we just want to look at the number of entries for a particular branch per event, you can use ak.num, and then this will give the number of entries per event. So in this case, this basically already existed because there was this n muon branch. But if it didn't exist, we could get the number of muons with this function. And so yes, for NumPy, there's no need for this because it would just be the same number over and over because it's rectangular. So you could just get it from saying dot shape on the array, and it would tell you the length along each dimension, which would be the same across the entire array. Okay, let me just take a look at the couple questions that came up. So can we use Uproot for current atlas analyses? It seems well mapped to root. Well, it could be easier to use. Yes, the answer is yes. I use Uproot for my atlas analysis. It's pretty well polished at this point and gone through several iterations, so it is very much ready for analysis. And does Awkward Array support user-defined data formats? Yes. So the main interface that I know of that exists for this is behaviors, which I won't cover it all in here, but there's awkward.behaviors. You can create classes that define how awkward arrays operate. So you can define functions on awkward arrays that are specific to whatever data format that you're using. So in that sense, it does. And Jim's connected. He's the awkward expert, so he can also
well, if
explain it.
Yeah, okay. I think you're going a little beyond even what the question might be asking. But can it read user-defined data formats? Most of them, yes.
Okay, so just looking through the comments. Okay. And right, exactly. Yeah. So Jim pointed out that if you use len on the tree, it'll give you the number of branches. It's only once you turn it into an array by saying like dot arrays that it will give you the number of events when you do len. Let's see. And okay, so here's one so I'm confused between using len and npravel. All right, okay, this is something that that I can mention here. So yeah, this would basically be the next step to say. So if this ak.num tells you the number of entries within each event, and if we wanted to know the total number of entries across all events for this branch, like the total number of numbers, then there's a couple ways we could see it, but one way is with this flattening, this ravel function. So what this function does is because it flattens across all events and turns it into a 1D array, then the length of this result, this flattened array, is the actual number of individual entries in muon PT. So there were 100,000 events to start with, but across those 100,000 events, there were actually 235,286 muon PT values. So that's the number of muons in this file. Right, okay. Ben mentions that this, for analysis, Uproot and awkward work for flat n tuples like nano AOD does not work perfectly for the more complicated structures like the full X AODs or mini AODs. And then okay, there's a question: how performant is it if you run over 10 million events? I mean, it's fast. I mean, it depends on exactly what the events are and what operations you run on. But when I get close to the end, I will run over the full data set because this is one thing that I didn't mention is for the purposes of up until the end, I'm just running on a very small subset, this 100,000 events, just to make everything very fast. So there's no waiting at all. But at the end, I'll just put in the full data set, and you can see how fast it goes. But it's pretty fast. Okay, so I'll go on. Let's see. Okay. So selections. So for Okay, so another form of selection or transformation on data that we can make is selecting a data. So we want to, so we've selected branches. We haven't selected events or elements within an event. So this can be done with masks. And I'll go through this pretty quickly because it's very similar to basically exactly the same as NumPy. So you can use comparisons like this, where you say branches, n muon branch equals 1. This is creating a comparison between the number of muons and 1. So this is going to give an array that has a bunch of values that tells us whether there is or isn't exactly 1 muon in the event. And we can use this Boolean array as a mask to pick out only events that pass this selection. So say events that have exactly 1 muon. So we can assign the result of this comparison to a variable like this. And then, so another way that, so a way that we could figure out how many events there are that have exactly 1 muon, in other words, figure out how many events pass the selections, we can do a sum over this mask, because the true values get converted to 1 and the false values get converted to 0 for the sum. So we can say there are a little bit over 13,000 events of the 100,000 that have exactly 1 muon. Okay, and then if we want to apply this mask to actually select branches based on this this selection, or events within the branches based on this selection, we just use this as a subscript. So again, just like NumPy, and say muon pt, where you can think of this this subscripting as saying where this single muon mask is true, and then it will pull out the muon pt of all these events that have 1 muon. And then we can also see, and so it's the number of these events is already here and up there. One more way we can see it is just with the length of the output, showing that we really have now removed, at least for this full expression here, once we applied the mask, we have filtered out events. It's not 100,000 anymore. Do masks support wildcards? So that's a question. Not in the way, so it doesn't support wildcards in the way that I've shown it here, but there are uproot functions that support filtering like branches and by wildcards. So if that's what you mean, like filtering branches by wildcards, that does exist. So then, right, okay, so then a few places here I just plot these selections just to kind of connect to when we actually make plots in these cases, all histograms. So it's very simple to plot awkward array or plot histograms of awkward arrays. The only thing you have to be careful about, just like NumPy arrays that have more than 1 dimension, you generally need to flatten an awkward array before you histogram it. This is kind of a rare case where it actually would work without the flattening, which is only because we've applied this single muon mask, so it's actually a rectangular array. But normally you need to flatten. So it's generally this is how we want to do histogram. And here I'm using Matplotlib to do the histogram. In the next talk, you'll hear about some libraries that are even more focused on creating histograms for high energy physics analysis. And so you can also do selections from a jagged array in the same way. You can do these comparisons. So in this case, I'm saying the absolute value of muon eta less than 2. So I'm making a jagged mask based on the muon eta, and then I get out a jagged array with Boolean values. And so I can do a sum of this mask, just like in the previous case, even though this is jagged, numpy.sum will automatically reduce all of the dimensions and just just give you a single number. So it's saying that there are 200 or plus 1,000 muons with an absolute value of eta less than 2. And then we can plot that just to verify that this is very, very large here, but just to verify that, okay, without applying the selection, I'll zoom out a bit, there's this broader distribution of eta, that's the muon eta, and then if you apply the selection, then you are really cutting out these muons that are out there in Ada. And all of the normal logical functions on arrays work just like NumPy. So things like the not operator and or, these operations are exactly the same. And so so applying not here would be like saying, selecting events or that do not have exactly one muon. And then you come up with, and you can say events, so you can say, you can combine masks with different dimensions. So like single muon mask is an event level mask, and the Ada mask is a muon level mask, and these broadcast just like NumPy arrays with different dimensions. So this works for awkward as well. So this is selecting events that have exactly one muon, that it has an absolute value of Ada, and specifically selecting muons that have an absolute value of Ada less than 2. And then you can also do it with. Okay, and then again, just kind of showing what these selections look like. If you make a plot of the muon PT using these selections, so saying requiring exactly one muon, and then making the selection on Ada, splitting by whether the absolute value of Ada is less than 2 or greater than or equal to 2, then you can see you get different distributions, and the muons that have a smaller absolute value of Ada tend to have a bit larger PT, which makes sense because they're more central. Okay. And then, so getting further into analysis, just kind of adding complexity as we go on. Okay, one thing we'll need is we're looking for dimuon events. So we want a mask that has a mask that selects events that had 2 muons. So a muon equals 2, gives us this 2 muon mask. And okay, so I finally get to the last package, vector. So this is where vector will come in. We want to construct the four-momentum, the length vectors for each muon. So there's a couple ways that you can do this. My favorite, didn't need to import it here. We've already imported vector at the top. But my favorite is vector.zip, for which you give a dictionary of arrays. So I give a dictionary with these keys are like PT, Ada, Phi, mass, and then the values are the branches that represent these values. And then this will, let's see. Okay, and then we can see this. Oh yeah, sorry, I can zoom in again. Oh, that was not a. So this is a special kind of array that comes out called a momentum array 4D. So you can see it's just a jagged array of momentum 4D objects. So it really is an array of Lorentz vectors. And so then we can select these vectors for events with exactly 2 muons. So this is just filtering out the events that don't have exactly 2 muons. And from this object, this vector object, you can pick out all of these components, including components that we didn't provide. So you can do, say, like .pt on this, and it'll give you the PT values. You can also do like .e to get the energy, which was not one of the inputs. So it actually will calculate any variables that can be calculated from these components. And okay, so getting up to the point where you're actually calculating the dimuon mask, I just split out the first and second muons in each event into these objects to make it a bit easier to read. So this shows you can slice awkward arrays with this same kind of notation as you can in like NumPy. so where there's a comma between dimensions. So I can, so here I'm picking out of this array with muon 4 vectors. I'm looking at all events, that's this colon here, and then just taking the first entry in each event. And then for this second object, I'm taking the second entry in each event. So this just gives me the first and second muons in these events. And now we can calculate things like delta R between these two objects for all events at once. So I can calculate the delta R between the first and second muons in each event. And that's what this is here. And then we can make a plot of that. Simple enough. And then we can see there's this nice peak at pi. So that'll be the nice clean dimuon events. And so I say we could use this. We could use the delta R to clean up the invariant mass distribution, but I just skip that for simplicity. So getting to the point where you actually can get the dimuon mass. So arithmetic of these vectors is supported just like these other functions. So I can just add the first muons vector to the second one, and I just put it into the sum P4 variable. So now I have an entry in this array for each of these events with 2 muons, and there's just a single 4 vector for each event. And then the last step to get the dimuon mass is we can just do a simple selection to make sure that they have opposite charge. So here you can pull out the muon charge for these events and then make a mask, an event level mask based on whether these muon charges are not equal. And then we can say that, okay, now that dimuon 4 vector is equal to this sum when the muons have opposite charge. So now we have it inside this object here. And okay, let me just take a look at the questions. Okay, the first one is a higher level one. So how does awkward scale with the number of events? Jaggedness, is it constant speed up with the number of events? Is there a sweet spot? Yeah, that I think Jim is probably best equipped to answer that question. So I'll just look at the next one. Does that mean that vector infers the physical meaning of the arrays from the dictionary keys? Exactly. Yeah, there's a specified set of keys that are allowed, but from the keys that are given, it will determine how to parse it as a 2D vector, or a 3D vector, or Lorentz vector. So you could give it, instead of mass, you could give it energy, and it would understand that. You just say E instead of mass. Okay. And okay, getting close to the end, and I'm getting, okay, so it should be pretty close to time. So I'll just go through maybe the rest of it here. So then, yeah, okay, I think this is actually a duplicate level here. These are already there. But then we can plot the mass of this dimuon object, this array. So this will just plot all of the muon, dimuon invariant masses across all of these events. And then you can see these peaks of the resonances. So we got to the point where we can see the mass peaks. And then we can see, okay, there are 37,000 events that went into this plot here. And then I just give this picture where I label the resonances. Okay, it looks the same. So we didn't change anything. And then, yeah, so in the last few minutes, I guess, I'll just talk about some of the more advanced features that, so I used arrays, uproot.open and tree.arrays to look at one file at a time and all of the branches. But sometimes you have multiple files and maybe the files are too large. So if you have to deal with multiple arrays, there are things like uproot.concatenate, which lets you, and then here's that like globbing, a wildcard thing that you can also use for file names. You can concatenate, say if I had multiple files that had the same structure, I could use this to put all of the branches together, concatenate all of the events. Or you can use uproot.iterate, which will step through the files by chunks of events, and you can set the number of events per iteration. And yeah, so this is also, this can help. This is something like this has to be done if you're using files that are too large to fit into memory. And there are other techniques that you can use to reduce how much you load into memory. You can use entry stop, which if you just want to look at the first 100 events, for example, you can just provide that to arrays, or you can just look at the branches that you want. So you can either select the branch from the tree and then say .array to just read out that branch as an array, or within the arrays function, you can give the list of branches that you're interested in. And the way that I normally used, kind of my preferred way, is to use lazy, uproot.lazy, which reads it provides an interface for all of the branches, and potentially across multiple files, but it doesn't actually read them until you ask for the data inside those branches. And let's see. Yeah, okay, so this is the full file, which is much larger. In fact, we can see what the length of this is. Yeah, it's so 61 million events. So you can try running that. It's still pretty fast. I think it takes probably a few minutes to run the whole notebook. Although maybe on this analysis facility, it's probably much faster than on my laptop, which would take a minute or two. To give you an idea of how much you can deal with. And then the last section that I'll just go through really quickly is, I mentioned how to read things from a file, but we also sometimes you want to create new arrays, vectors, new files. And so arrays are very easy to make, just like np.array. You can do ak.array, just as a capital A, and then you just can give it some list style array, and it'll turn that into an awkward array. Vectors, you can make individual vectors with like this dot object, and we've already seen how you can make arrays of vectors. So this is exactly the same as what we did before. And a nice, relatively new feature within the past several months with the most recent versions of Uproot is that you can make new files, new root files, and write to them. So there are things like uproot.create and recreate and update that correspond to the options in the same options in T file. So you can recreate this new file, and then it shows I've made a writable directory. And then you can assign objects to keys within this file. And then this is the way that you write to the file. And so that you want to use this like with interface, kind of like when you do like with open something as a file, you can use with uproot.update here to put this array into a file as a tree, and then just to show that you can now read that tree back. And you can also do this with histograms. So like if we wanted to save the dimuon mass histogram into a new root file, you can do this, where I'm just using numpy.histogram. And so Uproot recognizes this and will convert to a th1d, I believe. So it'll interpret as the th1, 1d histogram. And then just to show, okay, now we can read this new file and plot it as a histogram. And of course, a very important comment here is that root can read these files as well, which is huge because it makes it easy to drop in an uproot-based replacement for some part of an analysis. And then even if the later parts of the analysis chain depend on root files, you can still, the uproot part is able to create the root files that can go into the input for potentially root-based code afterwards. And then at the end, I just mentioned the links to all of the repositories and the documentation, which have links to other presentations and tutorials. Okay, and yeah, I think I'm at the end of my time.
Perfect. Thanks a lot for this overview, Mason. We had 2 more questions on Slido, but I think Jim is already answering them in the chat. So if there's follow-up, we can continue in the Zoom chat. Thanks again. This was great to see this overview, and we're going to continue on our agenda now with another set of packages. Andre is going to